So, good morning. This is a re-recording of Statistical Physics Lecture 11, which had audio problems. So, I'm just re-recording it and I will share it with the class. Okay, so today we begin our study of magnetic systems. And so, let me remind you of something which we did last lecture. And we discussed something called the Bohr-Van Leeuwen theorem, which basically states that in classical statistical mechanics, there is no magnetic response. And we saw the argument by computing the partition function with the magnetic field turned on, and we showed that it was independent of the magnetic field. And so, for instance, magnetization, which is given as the derivative of the log of z, or anyway, it's determined by some derivative of b, one derivative of b, and that vanishes. So this is the way the proof went. And so let us now revisit that again, and we will try to see how to put quantum mechanics into the story, and so that we can describe real world materials. Okay, so let us begin by looking at the Hamiltonian for a free particle of mass m and charge q. Okay, so in the presence of a magnetic field which is B, which we write as curl of a vector potential. And the key point to remember is from your classical mechanics course is that the Hamiltonian cannot be written in terms of B, but rather in terms of A, the vector potential. Okay, so this is a non-trivial fact. Okay, so now we can ask what is the vector potential for a uniform or a constant in space, spatially uniform magnetic field, and spatially homogeneous is what I should say, I guess. And in that situation, you can see that A is actually not. Let me correct this. So it is half B cross R. Okay, and so this is an exact formula when B is independent of spatial coordinates, so it's constant in your region of space. But of course, we can even for non-uniform cases, the above formula is an approximation. So again, it should be B cross R, not R cross B. So okay, so I was just checking if this formula was correct, so I'm fixing that. So A is half B cross R plus terms which are which depend on derivatives. In stands for involving. So let me write that properly. Derivatives of B. Okay, so we have now a formula which is at least approximately true, and in some special cases, so in experimental situations it can be made completely exact. Okay, so H is what we wrote for a particle of charge Q and mass m, and if you expand it, so of course the zeroth order piece when there's no A is just a standard p square upon 2m, but then the correction term is minus qm into p dot A plus there is a term of order A square. Of course it is there, and that was important for us to prove Bohr-Van Leeuwen's theorem. So, but for today, for now, we'll just ignore that term. But let's look at P dot A, which is half into P dot B cross R. So here I got it correct. No wonder. Okay. So now we can use the standard vector identity. We can cyclically permute these things. So B, I bring it here. R comes here and P goes here. But what is R cross P? It's the orbital angular momentum. So P dot A is just half B cross L. So if you plug it back into this term and replace P dot A with half B dot L, we get the Hamiltonian in this particular form, where we see that the magnetic field is coupled to the orbital angular momentum. And again, going back to the first principles, we can identify this with the magnetic dipole moment of the particle. Okay, so this combination Q vector L upon 2m can be identified with the magnetic dipole moment. Okay, so this is what, and I'll use the symbol mu for it because m is used for mass of the particle, so it will get overused. So mu is proportional to L orbital angular momentum with a prefactor which is q upon 2m. Okay, q upon 2m is important. Remember this, or I'll remind you later. Exercise, you can actually prove this using standard formulae for the dipole moment that you derived in electrodynamics. So if you remember, if you have a current loop, planar current loop or something like that, the magnitude of the thing was given by I times the area of the loop, and the direction was, either there are two possibilities, and you use kind of some thumb rule or whatever to fix it. But so that is the way you would have defined it. But for you can also define for a instantaneous magnetic dipole moment of a charge in motion, and roughly speaking, IDL will get replaced by Q times the velocity. Okay, so if you work it through, again you will get the same formula. Okay, so it's worth playing with that. So now what we are going to do is we'll ignore the a square piece, and we will we'll look at we could look at a truncated Hamiltonian, which just is p square upon 2m minus mu dot b. Okay, this is a standard interaction which you've already seen. Even in high school, I think it is given. And this is very good for weak and slowly varying in space magnetic fields. Okay, so if these two things hold, that means we can, the terms we have dropped out are not important. Okay, so this is something which you should bear in mind. Okay, but if you're going to have very, very strong magnetic fields, you better go back, put back the quadratic guy and work with it. Okay, so we know that this interaction with the magnetic field has lowest energy when mu and b are anti-parallel? No, when they are parallel. Okay, so again, I'm sure somebody would have figured out in class if they could hear me. Okay. Okay, so at low temperatures, it leads to a magnetization as seen in the problem sets that we were given out in school in the earlier weeks. Okay, so one more thing is in classical mechanics, orbital angular momentum can take continuum values. So its magnitude can change smoothly. Of course, direction also can change. It can take any direction, any magnitude. Okay, so for instance, we fix the magnitude of L, then the direction can take any arbitrary value. So any point on a unit circle will give you a unit vector, and that can be taken to be the direction of the angular momentum. However, in quantum mechanics, again something you would know, L is quantized such that L square is equal to L into L plus 1 times h bar square. So the fact that it is quantum is reflected in the fact that there is a h bar in the story. Okay, and h bar, if you remember, has the dimensions of angular momentum. But what to remember is that what are the allowed values of L, and these are the allowed values. L can take 0, 1, 2, 3. So it is like positive, but no, it's non-negative is the correct statement. Non-negative integers. Okay, so 0, 1, 2, 3, etc. These are the only possibilities. So L square is quantized. There's a further thing. So if you focus on one component of L, usually it's taken to be, LZ, but we can pick a unit vector n hat and ask how, what are its possible values. So for fixed L square, it can take only 2L plus 1 values, and this is usually called the M eigenvalue. But I won't use M. I'll just write out what the eigenvalues are. So these are the eigenvalues. Minus LH bar, minus L plus 1 H bar, so on and so forth, to LH bar. So you can see that there are 2L plus 1 possibilities if you fix the value of L square. Okay. But there is quantum mechanics has much more things in surprise. So you would think, this is good. L square is quantized and we are done. But there is a surprise, and the surprise is that fundamental particles such as the electron carry another angular momentum, which is called spin angular momentum, and the symbol that is used for it is S. And in your classical mechanics course or elsewhere, you would have heard about Noether's theorem, which says that for every continuous symmetry, there is a conserved current. And so in the angular momentum is associated, is considered to be the Noether current for rotational symmetries. Okay. So, and we show that for a particle, you get that angular momentum L, orbital angular momentum is what you get in usual cases. But if you look at quantum mechanical treatments or quantum field theory treatments of particles like the electron, you get the conserved current is not L, but it's a linear combination. It's this linear combination. It's a linear sum of orbital and spin angular momentum. So I'm giving it a symbol J. This is kind of semi-standard. I won't say it's standard. And so J, which is L plus S, is the conserved Noether current. I mean, you don't get L or S. You get both of them put together. Okay, so that is the first surprise. So in some sense, it says, so if you take something like the electron, it has spin, which is half. Okay, that's also a surprise. So that's what. So S square can take half integral values as well. So let me just fix this. Half integral values as well. So this is the surprise. So of course S square. So we'll use a little lowercase letters, little s into s plus 1 h bar square. So nothing different. But now if you look at what are the possible values of S, it is 0, half, 1, 3/2, so on and so forth. So half integral values which were not allowed. So when we look at L square, here we see it was 0, 1, 2, 3. There was no half, there was no 3/2, no 5/2, so on and so forth. But what you find is that these are also allowed for spin. An electron in this setup has spin half. So then we would like to ask, how does a spin couple to a magnetic field? Okay, so then we can just put a guess. So this is an analogy with how L led to dipole moment, magnetic dipole moment. We can define mu spin to be Q upon 2m times S. But we'll include a factor. We don't know that at least this will be a proportionality factor. Maybe there'll be some other thing. So there's some fudge factor. We don't know this answer. In principle, if you're in first principles, you can derive it in some cases, as I just mentioned. We just call this, experimentally you can determine this. So we call this the Landé G factor or the Landé factor. To be honest, it's a fudge factor. Okay, there's no derivation here. Okay, but for the electron, one can show that at least to leading order, there are corrections of order alpha prime, which is the fine structure constant, but those are quantum corrections and pretty small. So for us, at least, we can take G is 2 from the Dirac equation. Okay, so this is what happens. But that's actually an interesting historical fact, which is that this factor of 2 goes ahead and the spin half. Okay, so Sz, if you wish, can take plus or minus half. So it will look like it can take values. If you put the G factor in, 2 into half is 1. So it will look like it can take half integer. It looks like it's taking integer values, which is plus or minus h bar. Okay, but that's not correct. Okay, so you might see the derivation of this in your relativistic quantum mechanics class, which is I think QM2 or whatever. It's done there. But the point to remember is that particles such as the electron carry an intrinsic magnetic moment due to spin, and it's given by this thing, and the Landé G factor need not be 2 for everything. Okay, so G is 2 for electron. Each case you have to ask such a question, but it is intrinsic. It's a property of the particle. Okay, so even if the particle were at rest, where the orbital angular momentum is 0, okay, it will have spin angular momentum. Okay, and so because electron has intrinsic spin half, you will never see it. It will either have plus half or h bar. If you measure it, you either get half h bar or minus half h bar. You'll never get 0. But of course, if you do statistical averaging, you can get 0 because one half can give you one half of your particles can give half h bar. The other can get minus half h bar, and you can get 0. Okay, and there's an important remark. There is no analogy that can be made by thinking, assuming that actually electron is like a top and it's spinning, and so that rotational angular momentum is behaving as spin angular momentum, but that is not true, because but that would be some kind of orbital angular momentum, and that quantum mechanically that can take only integral values. So I mean that picture, even if it's given in a book, is wrong. Okay. So this is something you have to remember, that spin angular momentum cannot be discussed in the framework of spinning as some internal, some mythical spinning object. Okay. So now we'll move on. So this is just to give you some background as to what are the sources of magnetic dipole moment. It's not just orbital angular momentum, it also can come from spin angular momentum. Okay. So this is something which you should remember. And so now we'll move on to materials, which are of course collections of fundamental particles like atoms, etc., coming together. So it's a much more complicated thing, and their behavior is of something of interest in general. And so what we want to look at is materials and their magnetic properties. So what we'll find is there are three kinds of magnetic materials that we will find. They'll either be paramagnetic, diamagnetism. Paramagnetism we have seen a little bit. You apply some external magnetic field and then you will turn on you'll see that the system will pick up some magnetic dipole moment, macroscopic that is. So it will pick up a magnetization. But diamagnetism is interesting. It says that it's kind of, so in paramagnetization, the spins try to line up with B. In a diamagnet, it's the opposite. Okay, and for instance, in a superconductor, magnetic fields are expelled out, right? So you can think of it as being a perfect diamagnet. It gives you exactly, the magnetization is such that it will cancel will create a magnetism which will cancel it. Okay, so diamagnets there. M is anti-parallel to B. Ferromagnetism is even more interesting. It says that there exist materials where even without applying external magnetic fields, it has a magnetic moment. So a bar magnet, you don't have to connect it, turn on some electric power or do something for it to be magnetic. And so what happens is that it has a magnetic moment intrinsically without any external inputs, external field being turned on. Okay. But so these are properties of materials at a given temperature, pressure, whatever, various conditions. You keep the conditions fixed. But now let us do something. Okay. So let's say we start increasing temperature. And what happens to a ferromagnet is that there is a particular temperature. You can look up what it's called. And beyond that temperature, it loses its ferromagnetism, and it becomes a paramagnet. So if you turn on a B field, again it will get back. So if you didn't have an external B field, the magnetization will go to zero. Okay. And we would like to answer these questions in a statistical mechanical framework. Okay. So this transition which I just mentioned from ferro to paramagnetism is an example of a phase transition. So I'll give you a few more examples of phase transitions. Okay, there are many, many more, but I'll just give you a few which you will be aware of. One is a liquid going to a gas, right? So as you increase temperature, a liquid beyond its boiling point becomes a gas. Similarly, a solid can become a liquid, and if you further increase the temperature, it can become a gas. It's possible to go directly from solid phase to gas without going through liquid phase, etc. So these are all examples of phase transitions. And again, we would like to understand all these examples also in statistical mechanics. Okay. And this is what we'll be doing in later lectures. But what I want to point out is there is a problem in describing phase transitions in statistical mechanics. We actually understand their thermodynamics. And so from thermodynamics, we know that at phase transitions, there is a discontinuity in some derivative of the thermodynamic potential. So when I say thermodynamic potential, it's the analog of say state functions with like the entropy or the internal energy in the isolated system case, or in the canonical ensemble, the Helmholtz free energy, or some other setup, it's a Gibbs free energy. So there will be a discontinuity. And there's a definition. So which the order of the derivative which is discontinuous. If the first derivative is discontinuous, you say that the order of the phase transition is 1. Say if you say the order of the phase transition is 2, it means that the second derivative is is discontinuous, and so on and so forth. So usually common ones are first and second order, but usually people club it into two things: first order and continuous phase transitions. Continuous phase transitions, the word continuous is that your first derivative is nice, so it's a continuous. So that's the rough statement borrowed from function space. And but there is a further refinement, which is second, third order among continuous phase transitions. But some people just usually continuous phase transitions imply second order. So first and second are the most common examples that we will see. Okay, so these are things which we know from thermodynamics. But there is a problem, and that's what I want to discuss. How do we see discontinuities in thermodynamic potentials in statistical mechanics? So remember that everything starts from the partition function in the canonical ensemble. So you write it as sum over all energies. Maybe there is some degeneracy, etc. And this energy is a function. It depends on all the external parameters that you would apply. I mean, like if that's a magnetic field, it'll depend on that, and so on and so forth. But Z is a sum of exponentials, and the energy is also a smooth function. So it's like a smooth function. So each term is a smooth function. All derivatives exist. Okay, so it's the infinity, as mathematicians would call it. And so there's a problem in the sense that sums of smooth functions you expect that since thermodynamic potentials are obtained from sums of smooth functions, and after that maybe taking logs, etc. But smooth function, log of a smooth function is smooth. So our expectation is that all thermodynamic special potentials are smooth in statistical mechanics, and so we cannot see a phase transition. We will never ever get to see discontinuities in the when we compute thermodynamic potentials in statistical mechanics. So this is a problem, but there's a resolution to that. And the resolution is the following, is that we need to take the thermodynamic limit. That is, we need to take n to infinity, and only then we can see this thing. So what I'll tell you is a mathematical resolution of this statement. And so let's look at that. So in mathematics, if you have a discontinuous function can be obtained as a limit, a Cauchy limit to be precise, of a sum of smooth functions. Okay, but so Cauchy limit requires that sum be infinite smooth functions. So a classic example is if you have a periodic square wave, and it's a periodic function with some period capital T, we can do a Fourier expansion of this, right? So we can write f of t equal to sum over a_n's. These are the Fourier coefficients, n belonging to z, e power 2 pi n t upon capital T. So this is the Fourier series for this thing. And the thing is, you can derive the Fourier series of this. But now if you look at this thing, any finite truncation of this sum will never ever will be always smooth. Doesn't matter if you take 10, 100, 1,000, million, there will always be a discontinuity. Actually, I would recommend, try this out. Okay, truncate and compare. So what I mean is make a plot of the final function, which is a square wave, and then you take its Fourier series and take the first 10, 100, 200, 1,000, whatever you can do, and plot them on the same thing, and you will see that, for instance, at this point, any sum will always go through 0. Okay, roughly the theorem is that we'll take the average of these two values, and we have taken it to be equal. Say if we take it to be equal, then the answer, it will always be at 0. Okay, you can check this for any value of the sum. But the statement is that once you take all the limit, the Cauchy limit is to truncate it, say, to some magnitude of n being less than or equal to some capital M, and then take m to infinity, which is the Cauchy limit, you will recover this function. So it's recovered as an infinite limit. Okay, so same story is that applies here. Discontinuities can appear in the thermodynamic potentials computed in statistical mechanics in the thermodynamic limit. So the thermodynamic limit is the Cauchy limit. It's a mathematical version of the Cauchy limit out here, and then you can do this thing. Okay, and I want to conclude the lecture with a very interesting point that an ideal gas can never become a liquid. Okay, so if you want to understand phase transitions for instance, liquid to vapor or liquid to gas transition, you can never do that with an ideal gas. So you have to work with real gases. So this is one more system. We will look at it later. Once we study phase transitions, really the para-ferro to ferromagnetic transition, we'll study that in some detail before we come to real gases, and then we will see how real gases, can actually admit phase transitions, and we can show how that works out. Okay, so this is all I have to say today. And today's lecture was mostly descriptive, but now in the next 3 to 4 lectures, we'll put a lot of meat into whatever I've said today, and we will see that phase transitions occur, and there is beautiful structure underlying the neighborhood of phase transitions. So classic example is that the liquid gas phase transition and para and ferro look very different, but they could be in so-called the same universality class, in the sense that there is a sense in which they are identical. Okay, so I'll stop here, and